Hi, good afternoon, everybody. Can somebody please confirm that the slide is visible?
Yes, sir, it's visible.
Yeah, thank you. Today we will finish off this topic discussions on what we have been considering in the last several sessions, the similarity session, similarity relations, and their applicability or the specific forms that they take in hypersonic flows. That's what we have been formulating. We will conclude that in this class. We will also look at um, a demonstration of it based on a numerical exercise. So, just to remind you, we started off with simplified forms of governing equations, steady inviscid equations. We transformed them based on the assumptions of small perturbations, that is, the perturbations induced by the body. We considered them to be small in comparison to the mainstream velocity components, and we added some other additional assumptions like Mach number tends to infinity. In addition to that, the slenderness of the body, the most important assumption, that is tau, or the inverse of this one, slender, that is considered to be the value of tau is considered to be very small. So which basically says that we are focusing on very slender bodies, and which means that that provided us a few more simplifications, which could transform the equations into a form in which we can have the relations for non-dimensionalized pressure, non-dimensionalized velocity perturbations, non-dimensionalized density, etc., all in terms of the parameter m infinity tau. That is, when we transform the equations, eventually we see that the non-dimensionalized pressure, density, velocity components, etc., they all have, or they are all functions of this parameter m infinity into tau. What is m infinity? The free stream Mach number. Tau is the parameter that we describe or the parameter that represents the nature of the body, that is the inverse of the slenderness, so the bluntness of the body, as we used to call it. So tau is assumed to be very small, so that's how we had simplified the whole series of equations. Now m infinity into tau. So what we say is that based on analysis of the whole equations and their boundary conditions, we state that, or we conclude that, keep in mind, we are not solving them. We cannot solve them still, because they are still partial differential equations. They are still coupled. They are still non-linear. There is no way that we can solve them without numerical methods. We are not moving to numerical methods now. But then, looking at the boundary conditions uh, and the forms of the equations, we can say that the solutions can be in the form of the non-dimensionalized pressure. For example, the non-dimensionalized pressure distribution can be a function of x bar, y bar, gamma, and m infinity tau. Let's look at, so I have written all the three there. And let's just focus on the first one. P bar is a function of x bar, y bar, gamma, m infinity into tau. Actually, we have gone over this. I'm just trying to uh, remind you about that. So what this means is that if for a given x bar location, for a given y bar location, the pressure, the non-dimensionalized pressure will be the same for two cases, that is two finely related bodies. Please remember I'm showing with higher included angles for clarity. Actually, we mean bodies with very slender, which are very slender. Okay, just for the sake of clarity, I'm showing them like this. So I have body 1, I have body 2, and if I were to look at pressure distribution, which is characterized on a non-dimensionalized location of x bar and y bar, not xy, x bar, y bar, then the pressure distribution in terms of the non-dimensionalized pressure will be the same on two bodies if m infinity into tau is the same for both. M infinity can be different for both. M infinity itself. This is M infinity 1, this is M infinity 2. So the free stream Mach number can be different. The included angle, which is basically a function of tau, or tau is a function of the included angle. So the included angle or the deflection angle can be different for the two. One can be theta 1, the other can be theta 2. But as long as m infinity into tau, tau is actually tan theta, we have seen that. So m infinity into tau, tan theta is the same, then the non-dimensionalized pressure can be the same for both, is what we conclude from the whole solution. So this enables you. So if I have some solution, or if I have some experimental data for a combination of m infinity and theta, then I can extend it to similar bodies, similar affinely related bodies at different Mach numbers. That's advantage. That's the utility of this relation. Okay, so similarly, I'm not repeating the whole thing for rho and u bar. It's all the same. Okay, so because we all see that m infinity into tau, the similarity parameter repeating in all these. So that's why we call it as a similarity parameter. As long as that product is the same, though individually m infinity is different, tau is different for two cases, as long as the product is the same, we can have the same non-dimensionalized pressure distribution. I repeat, non-dimensionalized pressure distribution. We are not saying that pressure, absolute pressure or static pressure will be the same. No, the non-dimensionalized form of it, the way that we have non-dimensionalized it, gamma, tau square, etc., we have non-dimensionalized it. The non-dimensionalized form of pressure will be the same for all bodies, as long as m infinity into tau is the same. Okay. So this is what we had stated as the implication of hypersonic similarity on affinely related bodies. That is, bodies which are similar in their shape, but then can be different in one scale, in one dimension. The scale of the length can be different. We have seen these examples. We have seen this functional relation, which is just restating the same thing when there is a small angle of attack. So this can be extended to, we have not done the derivation for it. I'm just taking the relation from the literature. That is for a small angle of attack also, this can be extended as long as alpha by tau is the similarity parameter. Alpha by tau. And this applies only for small angles of attack. So when you have a small angle of attack, in addition to x bar, y bar, z bar, gamma, and infinity tau, you have an additional similarity parameter, which is alpha by tau. And we have just restated them in terms of pressure coefficient Cp by tau squared. In terms of pressure coefficient Cp, where again Cp we are just rewriting it in terms of P bar, where P bar is P by gamma infinity square tau square P infinity, and we just rewrite that, and the same relations can be written in terms of Cp by tau squared. So Cp divided by tau squared can be written as x bar, y bar, z bar, gamma, m infinity tau, alpha by comma at alpha by t when there is a small angle of attack. This is, and I guess we have discussed this graph and the similarity, the way that similarity is expressed in that, or rather, is visible in that graph in terms of two different Mach numbers, two different bodies, but the points in terms of the L by D, that is non-dimensional length, percent nose length, etc. They have given. They all fall on the same curve. They all fall on the same curve, which indicates that as long as the similarity parameter holds, the non-dimensional value Cp, which is on the Cp by tau squared actually on the x y axis, that becomes the same for both the bodies at the corresponding locations. Okay, and this graph also, which is some limited experimental data, we have discussed this also, the flagged points and the unflagged ones, etc. They are falling on the same curve, which is also a demonstration of the applicability of similarity concept in slender bodies. Okay, now with that, now I'm trying to show this with simple a series of calculations actually based on oblique shocks based on oblique shock calculations on a wedge shaped body. I'll explain this. I'll explain the steps. I'll explain the calculation the way that I have done, and I'll present some data also. Probably later I'll formulate it as for a different set of conditions and give it to you as an assignment so that you get a feel for doing it than just watching it my calculations, because when you do it, I'm sure that you will get a better feel for what we are talking about. So right now, please read that what is written there. Consider flow across a wedge shaped body. Now read that once again. Flow across a wedge shaped body. So for now, for the clarity of the concept, we are focusing our attention to a wedge shaped body. This wedge shaped body is not new to us. That's something which we always have been considering from compressible flows onwards to describe the oblique shocks. So when you have a wedge shaped body, you use shock theory to compute Cp by tan squared theta. Now, what is Cp by tan squared theta? Cp, we know the familiar pressure coefficient, the non-dimensional form of static pressure, Cp, right? The pressure, we have seen the definition of Cp, P minus P infinity divided by half rho V squared, rho V infinity squared, rho infinity V infinity squared. So that is Cp, and tan theta squared, tan theta, that is related to tau. We have seen that earlier, that L by D, or rather the other way around, D by L. So that tan theta is what we call use as the bluntness ratio tau. So Cp by tan squared theta as a function of m tan theta, that is m tan theta is nothing but n infinity into tau. So Cp by tan squared theta, m infinity into tau. So what is the importance of it? That's what we had just previously discussed. M infinity into tau is a similarity parameter. Cp by tau squared is also a similarity parameter. I'll get back to that slide. Cp by tau squared. Sorry. Cp by tau squared and m infinity by tau. Just disregard this alpha by t for now, because we are not considering angle of attack in this problem. So neglect that. So we don't have angle of attack. So alpha by t is not there in the picture, which means that Cp by tau squared can be expressed as a function of x bar, y bar, z bar, gamma, m infinity into tau. Now the question is between Cp by tau squared and m infinity into tau. And what does the similarity parameter say, or similarity concept, or what we have concluded from similarity analysis? The statement is that if m infinity into tau is the same, I repeat that, if for two bodies m infinity into tau is the same, then at a given x bar, y bar, z bar, Cp by tau squared will be the same. Okay, so you please be sure about the statement. If for two bodies m infinity into tau, the free stream Mach number can be different, a different tau can be different, but as long as the product is the same, the value of Cp by tau squared, which actually represents the static pressure distribution, Cp numerator is the static pressure distribution. So Cp by tau squared will be the same for corresponding locations of x bar, y bar, z bar, is what is basically what we conclude from the similarity analysis. Now let's go back to the problem. So when you see Cp by tan squared theta here, understand it as Cp by tau squared. Similarly, m into tan theta means m into tau. Okay, so those are the parameters we are just. Now what is stated here is consider a wedge-shaped body and check the similarity concept in terms of the validity for slender bodies. Here we have considered slender bodies as theta equals 2 to 8, which is a reasonable range actually. Usually up to 8, they call it as, it's not a hard and fast limit, but usually say an included angle of in degrees. to 8 to sometimes even to 10 can be reasonably considered as a slender body. Okay. No, if you ask whether there is a limit for slenderness, etc., probably not. But then usually this is considered in hypersonic flow applications as a range of slenderness. Now, so what we can use free stream free stream static pressure as 10 kilopascals, gamma is 1.4. So for under these assumptions, we have to see Cp by tau squared is a function of m tau. That is, as long as m infinity into tau is the same, Cp by tau squared is the same, is what we have to examine. If we are able to show that, then we are saying that, yeah, we are at par with, or we are in agreement with the conclusions of validate this one, hypersonic similarity. Any questions so far before I show the calculations? And I hope you are able to sort of follow what we are trying to do to achieve. Let me know if there is any question. No, fine. And I'll just show the calculations. I'll try to explain the steps of it so that, say, theta is a measure of tau. Keep in mind, tau, L by D or D by L, right? So the slenderness is defined also by the included angle, tan theta, etc. So I have taken some values of theta 487 2. I'll come to that. So anyway, they are all within the range of theta equals 2 to 8. Please neglect the second column, that's just theta in terms of radian. As I always say, I do this in Excel, so and Excel needs theta in radian when I put tan, etc. So I just, for sake of convenience, I insert an additional column converting it to radian. So you don't even look at it. Not okay. Then m infinity, the all important parameter. So I'm starting with m infinity equals 5. That's only because I just consider that I just take the hypersonic initial and hypersonic region. So I just took it as 5. So theta is 4, m infinity is 5. P infinity is given in the problem as 10. So I just reproduced it here. P by P infinity is calculated from I used that university app that we have seen, that is which gives normal shock relation, sorry, all compressive flow relation. So I just used oblique shock relations in that, in which I gave the value of theta as 4, Mach number as 5. So I got P by P infinity. So that this I got from the tables, shock tables. Now, if P by P infinity is like this, then obviously, since I know P infinity as 10, I can calculate the static pressure. If I know static pressure, I can calculate Cp, because Cp is just a function of static pressure, because we know the free stream values, gamma, n infinity, this one, etc. So v velocity, I just took, I guess I used T equals 300 Kelvin or so to calculate the velocity. So we know Cp, which is a non-dimensionalized static pressure. So no big deal in the calculation of Cp. So it's basically, it is coming from the oblique shock relations. Now, once I know Cp, I just calculated Cp by tan squared theta, which is nothing but Cp by tau squared. Cp divided by tau squared. Tau is tan theta. Theta is given. I have started off with 4. So Cp by tan squared theta is what I have listed in this. Then I also calculated what will be the corresponding m infinity into tan theta, m into tau. That is basically m infinity tau, the similarity parameter. So Cp by tau squared, I got Cp from oblique shock calculations. Tau is from the geometry, m infinity from the free stream conditions that I have assumed, tau from the geometry again. So the last two columns give Cp by tau squared and m infinity into tau. Okay. Now, so that is for one set of theta, set of theta and Mach number. Now, when I go to the next theta, I took theta as 8 degree. Which one? Sorry. I think it is. Yeah. The second value is 8 degree. When I take theta is 8, I should be careful that I cannot take any m infinity. Keep in mind, because my m infinity into tan theta, m infinity into tau has to be the same for all cases. So the first case, I have the value of m infinity into tan theta given here. So if I change tan theta, I should change m infinity in such a way that this product has to be the same. So for all cases, I fix my m infinity into tau, because that's a deal. The deal is that your similarity parameter has to be the same, the product. So m infinity into tau, I maintain the same, and then I use the corresponding value of m. So here I get a lower value of m because tau is high. So I use m infinity into tau. I use the different value of m. I again repeat the same calculations as I did earlier, p by p infinity from the table, p from this ratio and p infinity, and then cp as I mentioned earlier, cp by tan squared theta, just by dividing it by the new value of tau squared, and then so this is the new value of cp by tan squared theta. Similarly for 7 and 2, and this is the variation that I get for cp by tan squared theta. You can see that the values, if you were to read 7.16, 7.61, 7.44, 7. Whatever, 7.07, I think. Yeah. So all of them were fairly close. Actually, they are not extremely close, because that is because we have deviated in these values from the hypersonic range. Actually, the intermediate two values are lower than hypersonic. But then fairly these values are close. Now remember, we have different values of theta, we have different values of Mach numbers, but static pressure is fairly close. Not static pressure, the non-dimensionalized static pressure Cp is, and Cp again normalized by tan squared theta, is fairly close. So this is what the hypersonic similarity also says. I'll show this more clearly or more accurately for higher hypersonic range, which I have done. I've repeated the calculation again. Yeah, I've repeated the calculation again for a different set of m infinities. I'll try to explain that also. So the same procedure. I stick to this range of Mach theta 4872. I take, so correspondingly I do the same calculations, with the difference that now I'm actually targeting at high hypersonic Mach numbers. So I start, instead of 5, I started with 25. So I have 425 that is theta for Mach number 25. Then the calculations of p infinity, p by p infinity, static pressure, cp, cp by tau squared, and m infinity into tau. All this will give me, and m infinity into tau. And then if I were to calculate this p bar, this earlier I had this stopped at cp. Now if I do the p bar, that is the non-dimensionalized p, I get it as 1.6579, etc. 1.65, just call it 1.565 or 66 or something like that. This 1.65 is the static, the non-dimensionalized pressure I get for m infinity 5, m infinity 25 and 4. Now to examine hypersonic validity, I go to another set of values. So I varied my theta arbitrarily to 8. But then I cannot vary m infinity arbitrarily. I need to make sure that m infinity into tau or m infinity into tan theta is the same. So what is this? I need to have the initial value is 1.75 m infinity into tan theta. So here also I should have the same value. If I need to have the same value, I calculated that my Mach number has to be 12. Still hypersonic, no issue. So the second Mach number that I took was 12. And then I repeated the whole calculation. And I checked at the value that I get for P bar. that is 1.64. So look at that. Initial was 1.65. The second is 1.64. I repeated the whole thing with 7. Theta is 7. Since I need to keep m infinity into tan theta same, I worked out that my m infinity has to be 14, which is still hypersonic. I do the calculations. I get p bar is 1.64. And then I repeat it for a lower value of theta 2, and the same thing I find out that the Mach number, since it is much lower, the Mach numbers happens to be higher, is 50. Anyway, I'm happy because it's hypersonic. So the higher in the hypersonic range, the better it is, because we have always followed the high hypersonic approximations. So then I do all these calculations. I see that I see that the p bar non-dimensionalized p is 1.65. So we see that, so it's all 1.65. So if I just almost take it to the side, this one, it's all 1.6566, 1.64, 1.66, etc. So that is the kind of the similarity, or the values are practically close, or actually or almost equal. So the p bar values, non-dimensionalized static pressure, is the same regardless of the variation in theta and m infinity, whereas as long as m infinity remains, m infinity into tau is the same. Now you should note this. Actually, it's a striking observation, because say 1.65 for m infinity is 25, m infinity is 50, a huge difference, right? It's twice. M infinity 25, m infinity is 50. The Mach number, the free stream Mach number is twice, and also m infinity is 12 and 50, 4 times, right? 12.5 or so. So 12.5 and 50, 4 times. Even then, that is even if the free stream Mach number is 4 times high, we see that the non-dimensional static pressure is practically the same. 1.641, 1.65. So very close actually. So that is the proximity, or that's the accuracy that we get as long as we follow the inviscid flow calculations. And this is what is observed from the non-dimensional grouping that we obtained based on the formulation, which is based on hypersonic small perturbation analysis. This is a utility of this method. So for different Mach numbers, you can calculate it in terms of the product of n infinity and tau, the similarity parameter. I have also added one row here just to show you the variation. That is, this actually we always say that tau has to be small. What if tau is high? That is, if I slightly jump into the blunt region 20. So I just took a different value 20, which is slightly on the blunt side, a higher value of theta. Then we see that when I just followed the same pattern of calculations, but then we see that there is gradual change in the MP bar also. Say all others were 1.6, 1.6, 1.6, etc., etc. Whereas the last one, when I varied it to, when I tried to move to a higher value of theta, then the value starts shifting. Now it is 1.55, etc. So the farther that I go, the lower will be the match in p bar values. So it again confirms that the concept is only applicable for slender bodies, small angles of attack. I have also plotted it so that you can probably visualize it easily, and just get rid of all this ink. Okay, so Mach number on the Mach number, that is m infinity here on the y-axis, on the x-axis, and p bar on the y-axis. M infinity, p bar. All that we are saying is that if you are sufficiently high, if your Mach number is sufficiently high, then the non-dimensional static pressure is going to be practically the same. You see this, almost constant, right? So in the hypersonic range, whereas at lower values blunt bodies. So when I move here, I had two things actually. I had two deviations. The body was blunt 20, and my resulting Mach number also was slightly on the lower hypersonic range. So both led to a deviation from the hypersonic similarity, the validity of hypersonic similarity. Whereas in the high Mach numbers and low thetas, I can say that the P bar, the non-dimensionalized static pressure, almost remains the same with free stream Mach number. With increase in free stream Mach number, provided that this is not unconditional. This is because I have kept M infinity into tau the same. So I'm not saying that the non-dimensional pressure will be the same for any Mach numbers. No, as long as the free stream, the product of M infinity and tau are the same, is the same, then the P bar will be the same. That's basically the statement of the hypersonic similarity concept. So, and that is what is demonstrated in this graphs. I think I should stop here. You have any questions, please? We conclude this in this session. I'll try to formulate one assignment later and give you so that you will get a better feel of it. Even otherwise, you can do this on yourself or by yourself, so that you get hands-on feel of what we are talking about. Any questions, please? If you don't have questions, we'll stop here today. Meet in the next class. Thanks to all of you. By the way, Viva. Some people have asked me when is Viva, etc. I'll first complete the everything engines Viva, that which I will be completing this week, and I'll put the schedule for hypersonic after that. So most probably I won't be starting it this week, but I request you to keep checking that the team's chat, this one. So if I have any update, I'll put there. So certainly next week we will have, and we will complete it, the hypersonic Viva, or the hypersonic theory Viva also. Okay, then. Thank you. Thanks to all of you. Bye.
Thank you.
Thank you, sir.
Thank you. Thanks. Bye.
So will the remaining Viva for air breathing engines be conducted today?
No, today not actually, because a lot of meetings are lined up this afternoon for me. So I'm not able to do that today. Actually, I would have liked to do that today. Tomorrow's I'll check and put the schedule in this one. Okay. Because there are some meetings tomorrow also, and I don't know the times yet. But as soon as I get a clarity on that, I'll put the schedule in the Teams box. Okay.
Okay. Okay. Thank you.
Thank you. Thanks.